Amino acids are like the protein's building blocks. There are 20 different types of them, and they all consist of an amino group, a chiral carbon, a hydrogen atom, a carboxylic acid, and a unique R group. This is what the structure looks like, and what makes amino acids different from each other is the side chain or R group. Other than that, they are the same, except for glycine, which has a hydrogen atom instead of a chiral carbon. With the Fischer projection, it is easier to notice the four unique bonds that the carbon atom has, as well as the difference between the L amino acid and the D amino acid configurations. These are called enantiomers, which are mirror image molecules that are not superimposable, and only the L amino acid is found in the human body.
Classification of amino acids. Amino acids can be classified depending on their pH, their charge, and their H bonding ability. One of these classifications is the nonpolar R groups. The characteristics are that they're highly hydrophobic, liposoluble, and give internal structure. Some examples are glycine, alanine, valine, leucine, isolene, methionine, tryptophan, proline, and phenylalanine. Another classification is the uncharged polar. Its characteristics are hydrophilic, hydrosoluble, no subdivision, hydrogen bridge, pH 7, charge 0, and they generally have an OH or an ACE. Another classification are the charged polar. They can be positive basic, which have an extra amino group, and the negative acidic, which have an extra carboxylic group.
A peptide is a chain of small groups of amino acids linked to each other by a peptide bond. Some examples of amino acids are phenylalanine, valine, glycine, and serine. The union between two amino acids is called dipeptide. From 3, tripeptide. From 4 to 10, oligopeptides. From 10 on, polypeptides. The peptide bond is made when the carbonyl group of one amino acid reacts to the amino group of the other amino acid, undergoing a dehydration or condensation reaction, as it produces a water molecule. This bond can be undone through a hydrolysis reaction.
The shape of a protein is very important to its function. To understand how a protein gets to its final shape, we need to know the 4 levels of protein structure: primary, secondary, tertiary, and quaternary. The primary structure consists of individual amino acids that join together in long chains by forming peptide bonds between their carboxylic group and their amino group. The secondary structure refers to local folded structures that form within a polypeptide due to the interactions between atoms of the backbone. The most common types of secondary structures are the alpha helix and the beta pleated sheet. Both structures are held in shape by hydrogen bonds. The tertiary structure is the overall three-dimensional structure of a polypeptide. It is primary due to the interactions between the R groups of the amino acids that make up the protein. The quaternary structure is made up by 2 or more tertiary structures.
There are several functions of proteins. The first one is repair and maintenance. Protein is vital in the maintenance of the body tissue, including development and repair. It is present in the hair, skin, eyes, muscles, etc. The next functions of proteins are creation of energy and hormones. If you consume more protein than you need for your body tissue maintenance and other necessary functions, your body will use it for energy. In the case of hormones, proteins are involved in the creation of them. These substances help control body functions that involve the interaction of several organs. Enzymes are proteins that increase the rate of chemical reactions in the body. Here we have 2 examples. One type of enzyme functions as an aid in digesting large proteins, carbohydrates, and fat molecules into smaller molecules, and the other enzyme assists the creation of DNA.